Good evening, Math 30-1. Gonna apologize first off for the tree frogs, but we're gonna see what we can do without them. So this is video for section 1 on our unit 3 or chapter 3, dealing with polynomial functions. So today we're just gonna learn what a polynomial function is. We're gonna discuss it a little bit with characteristics and how to identify them. So to start off, there is this definition, which at first looks a little bit intimidating, but is really rather straightforward. All these a values in front are just coefficients. They're real numbers, as identified here. So the fact that it has a little subscript with an n is just telling you whether it's in the first term, second term, third term, fourth term, and so forth. But they're just real numbers. Any number that you've seen so far currently in math, in your math career, has been a real number. X is the variable. Okay. For there to be a polynomial, x needs to be the only variable. So we're not going to have more than one variable here. You're only going to see either x, or if we changed everything and had m, it's just consistent variable. And then the last requirement for a polynomial is this n that you're seeing in the exponent. N needs to be a whole number, non-negative integer. Okay, so again, a whole number, non-negative integer. So specifically, it can be 0, 1, 2, 3, 4, 5. It cannot be the exponent of -1 or -4. It cannot be a fractional exponent, such as 1/2. So we're going to go through a list of functions here. There's 6 functions. I'm going to determine whether they're polynomials or not. First function here is x squared plus 3x plus 2. This is definitely a polynomial. Okay, this is the most one of the most common polynomials that you have dealt with so far. It's a quadratic function, and quadratics are types of polynomials. So the reason why is that we have, first off, a real number coefficients. All of the numbers in front of the variables, even this last 2, this constant term, are real numbers. We have consistent variable. In most of the cases that we're going to deal with, they're going to be consistent variables anyways, but it's important to identify. And the last, and probably the biggest giveaway as to whether it's a polynomial or not, is our exponent. And so if we look at our exponent, we can see that they're all whole number, non-negative integers. Specifically, here we have x squared plus 3x. So this second x has an exponent of 1. And I want to identify this last term, this constant term. Really, it also has a variable x, but that x is to the exponent 0. Okay. So keeping that in mind with our constant terms, again, we can see that all of our exponents are whole numbers and non-negative. So whole number, non-negative integer, exponent. Okay, those are the 3 criteria. So we're going to continue on with the other 5 functions and determine whether they also meet this criteria. Second function, we have this square root x to the 5th plus 3x squared plus 6. Well, first off again, this 6x looks like it's going to be 6 is a real number. X is going to be to the exponent 0. Okay, so which is why we don't necessarily need it there. 3x squared. Okay, 3 is a real whole number. Squared is a whole number. Okay, so far we're good. This first term though is what causes us problems. Whenever you have a square root or a radical in front, you need to think back to what we did in Math 20-1 and realize that radicals are actually a type of exponent as well. So this first term actually can be expressed in this way. X to the 5th, and instead of writing the square root, it is the fractional exponent of 1/2. The rest remain the same. So when we simplify this first term, we actually have x to the exponent of 5/2. Remembering that when we have it, remembering that when we have an exponent taken to another exponent, those two exponents will multiply. So we have a fractional exponent. It is not a whole number exponent, which as a result means that this function here is not a polynomial. So the answer to that is no. And the reason why, non-whole number exponent. Moving on to the next one. G of x is equal to 3/4 x cubed plus 9x squared plus 10x. 10, real number, x, okay, or a consistent variable, exponent 1. 9, real number, x, okay, consistent variable, exponent 2, okay, whole number. First term, 3/4. 3/4 is a real number. We have a consistent variable of x, and we're taken to exponent 3. So we have real number coefficients, we have a consistent variable, and our variables, our exponents, are all whole numbered non-negative integers. This is a polynomial. Meets all three requirements. Function 4. Take a closer look at this one. Again, we have a constant term. That one's fine. 3x. Okay, that's fine. 8x squared. All right, that's also fine. But we run to the issue here with the first term again. We have a negative exponent. Again, that doesn't meet the requirement for our exponent. So this one is not a polynomial. And again, it has a negative exponent. Function 4, y is equal to 2. Remembering that with constant terms, we could really write this as x to the exponent 2 times x to the exponent 0, which means that we have a variable of x, we have a real coefficient of 2, and we have a non-negative whole numbered exponent. So we could consider this a function as well. It's actually a linear function. It'd be a completely horizontal line, which also meets our requirements. So the answer to that is yes. And y, again, meets all three requirements. And the last function. We have 3x squared plus 6x plus 10 divided by 2x. Before we can answer this one as to whether it's a polynomial or not, we need to simplify. So we're going to take each term in the numerator and divide it by the denominator. Once we simplify each term, in this first one, we're going to be left with a coefficient of 3/2, or 3 divided by 2, which is perfectly fine. It's a real number. X squared divided by x just leaves us with a x. Okay, so it's a consistent variable. We're using x again. It's exponent of 1, which is also fine. 6 divided by 2 gives us 3, and x divided by x leaves us with 1. So we just have a 3 there, which is fine as a constant term. Where we run to the problem is in the last term here, is 10 divided by 2 is 5, but we're going to be left with 1 divided by x, which can actually be expressed in a different way. Whenever you have a variable in the denominator, you can express that whole fraction as your variable to a negative exponent. So 1 divided by x is also can be expressed as x to the exponent -1, which again causes issues because now we have a negative exponent. So this last one is not a polynomial, and why? Because it has a negative exponent. So it breaks the last rule. Okay, so those are hitting briefly on identifying polynomials. So we're going to move on to some key terms about what a polynomial is and our key features of polynomials. Key features of polynomials. We have key terms. First off is the degree. We're going to use the term degree to help us refer to what type of a polynomial it is. Specifically, it's the largest exponent on our variable x. So in our example, if we look below, x to the exponent 4, okay, the 4 is the largest of the exponents, and so that way it means we have a degree of 4. Leading coefficient. The coefficient is it's the number in front of the variable with the largest exponent. So in front of this x to the exponent 4, there's a 1. So we have a leading coefficient of 1. Constant term is just our number that has no variable, or at least there doesn't seem to be a variable. So that means we have a constant term of -6. And end behavior. End behavior is, in this case, I'm going to explain to you just positive, positive. We'll identify that a little bit better shortly. But end behavior is what does our function do as x becomes very large negatively and very large positively. So as our domain approaches negative infinity or positive infinity, what is it that our function is doing? So let's take a look at specifically some of the functions that we've mentioned. Function number 1, it's a linear function. Linear functions are the ones that you've dealt with the most. Again, if we look at the graph calculator, I've graphed 2 other linear functions. They're lines. Okay, leading coefficient. Okay, it depends. In this case, it's just a positive leading coefficient. In the right-hand side, it's a negative leading coefficient. With a positive leading coefficient, we have a positive slope. With a negative leading coefficient, we have a negative slope. End behavior. Okay, so in this first one here, it starts, when we look here on the negative side, or as x approaches negative infinity, our function is also negative. As we follow the function to the right, or to where x becomes positive infinity, our function is positive. So we have a negative, positive end behavior. Looking at when we have a leading coefficient that is negative, our end behavior starts positive on the left-hand side and goes down to being negative on the right-hand side. What I'd like to point out right away is that our leading coefficient, if it's positive, it tells us that the right-hand side of our end behavior is going to be positive. With a leading coefficient that is a negative, it tells us that our end behavior on the right-hand side is negative. So the leading coefficient can help us determine what our end behavior is. Constant term. Okay, the constant term is also going to be our y-intercept. So whenever we look at a polynomial, whenever that constant term tells us what the y-intercept is, and in this case on my graph it's 2. In this case as well, my constant term is 2. The domain is going to be all real numbers. The domain for the second one is also all real numbers. And our range also is going to meet the requirement of all real numbers with these functions. X-intercept. Okay, what I'm focusing on here is not exactly what is the x-intercept. We're going to get to that later in this in the course. But right now, just how many x-intercepts can we have? With a linear function, we can have 1. Can't have 0 unless you have a completely horizontal line. But in most cases, you're going to have an x-intercept of 1. And in that case, that means that we have no maximum or minimum. Okay, so none applies. It's not going to reach some maximum point or some minimum point. Moving over here to the quadratic function. Quadratics, okay, they are the parabolas that we've dealt with in the past. On the left-hand side is all of our positive parabolas. They're facing upwards. And on the right side, it is going to be negative. Our end behavior. Again, if we look at our coefficient, we know that our right-hand side, our end behavior is going to be positive. With even degreed polynomials, okay, so this one's quadratic, it has a degree of 2. Both of our end behaviors on the left side and the right side will be the same. So if we know that the right side is going to be positive, that means that the left side is also going to be positive. So if we look at when we have a negative leading coefficient, it means we're going to have both a negative end behavior. Okay, the right side is going to be negative. We can find that out from the leading coefficient, and the left side is also negative because it's an even degree, so they're both going to be the same. Constant term, okay, again, it's just our y-intercept, and as you can see in the graphs, if you look closely, it's changing. I'm shifting the parabola either upwards or downwards, and so the constant term is going to change. Same thing over here, but remember, it's again just our y-intercept. In all these cases, it's going to be the y-intercept. So it depends really on what the parabola is, but yeah, every case is going to be different. Domain, okay, is going to be a set of all real numbers in both cases again. But the range here is going to be a little bit different. We're going to have the case where we're going to have the case where y is greater than some minimum value. Okay, so you need to find out where your vertex is, and that's going to provide you with some minimum value. Similarly with our range in the other function, it's that y is going to be greater than some maximum value, or less than some maximum value. It's not greater than, it's going to be less than. That maximum or minimum value will not necessarily be your y-intercept. In the graphs that I've currently done above, my minimum on the left side was my y-intercept. On the right side, my maximum was my y-intercept. As soon as you translate these parabolas either left or right, that is no longer the case and no longer applies. So you cannot just depend on the y-intercept or your constant term to tell you where your maximums or minimums are. Number of x-intercepts. Again, the reason why I did 3 graphs here is to demonstrate the number of x-intercepts that we could have. In the first graph here, we have 0 x-intercepts. In the second one, the parabola just touches the x-axis, so we have 1. And in the third case, the parabola drops below the x-axis, providing us with 2 x-intercepts. What I want to identify again at this point is that the largest number of x-intercepts is going to be the same as your degree. So in the linear function, it had a degree of 1. It meant that we could have a maximum of 1 x-intercept. With quadratic function, or degree 2, our maximum number is going to be 2 x-intercepts for both our positive and negative cases. This trend we're going to see continuing on for higher degree polynomials as well. And once we get into degree 3 polynomials, you're going to see the trend that carries on. With a positive coefficient, that means that we're going to have a minimum. And when we have a negative coefficient, that means that we're going to have a maximum. Okay, so let's continue on to talk about the third type of polynomial. So this can be the cubic function. It has a degree of 3. Now, I'm going to demonstrate to you, I'm going to let you graph these two functions in both these cases, both the positive and negative case. And I'm going to let you try and graph those in there. But what I want to identify is, if I go over to my calculator over here, what the general shapes may look like. The green function here is the base cubic function. That is y is equal to x cubed. It comes up from the negative. Okay, when it gets close to the origin, it flattens out and then increases positively upwards. Okay, so first off, the end behavior we could talk about is negative, positive, which again we could have identified using our leading coefficient. What I want to demonstrate, though, in a similar way, I've created this orange graph. The orange graph demonstrates that when we start to translate this cubic function, or this third degree polynomial, sometimes it will result in a basically an extra loop where it looks like we have two parabolas that have been fused together. So our function increases to some maximum point and then decreases to a minimum point and then keeps going up. This maximum and minimum point are not absolute maximums and minimums. It's these little bumps in the road. But because our function continues going increasingly positive to the right and increasingly negative to the left, it means that we have still no maximum or minimum, or I should say absolute maximum or minimums. So we're going to still say that does not apply for maximum and minimum in both cases. X-intercepts. Let's go back to domain range. Domain range is still going to be a set of all real numbers. And similar to a linear function, we're also going to have our range be all real numbers. And I'll let you finish off the range in the second one. Sorry, I guess I overlooked the fact that on the negative side, my end behavior would be positive, negative. Again, I can find out that it's negative from the leading coefficient. And with odd degreed polynomials, so this is the third degree, 3 is an odd number. With odd degreed polynomials, my behavior, end behavior, is different in the left side from the right side. So my right side I can find out from the leading coefficient, and my left side is just going to be the opposite for odd numbered polynomials. X-intercepts. Depending again how this function is translated, there is no way that we can have 0 x-intercepts. So 0 is not one of the options. With odd numbered polynomials, you cannot have 0 as a possibility for your number of x-intercepts. So we only have 1, 2 is an option, and 3 is an option. Again, the degree tells me what my maximum number of x-intercepts is. So in this case, it's going to be 3, and that's in both cases. So when we go on to quartic, okay, a quartic is a degree of 4. I can show you here on my calculator. Here's what they can look like. The most basic, y is equal to x to the 4th. You can graph it on your own calculator. It looks kind of like a parabola, but it's flattened out on the bottom. Okay, so this red one here. And then when it gets transformed, it can look like this blue one, where again, similar to a parabola, it decreases and then kind of continues back the opposite direction. But it has these extra little bumps in the middle. Similar to a parabola, it ends where it starts. So, for example, this left side here is my positive leading coefficient. My end behavior is going to be positive, positive. If it were a negative leading coefficient, I would have the end behavior of negative, negative. Okay, it resembles kind of a parabola. Okay. Or a quadratic function. Constant term is still our y-intercept, so I won't divulge in that. Our domain is still going to be all the real numbers. That's not changing. We are not restricting the domain at all. So in all these cases, we're going to have our domain is all real numbers. Our range, though, is going to be, again, like before, that our y value is greater than or equal to some minimum value. Our range with a negative leading coefficient is going to be less than or equal to some maximum value. X-intercepts. With even numbered degreed polynomials, we can have x-intercepts of 0, and then we have a maximum of whatever the degree is. So we can go all the way up to having 4 x-intercepts here. So 0, 1, 2, 3, and 4. With even numbered functions or even numbered polynomials, we can have maximums or minimums. So in this case here, it's going to be a minimum, as we've already indicated in the range, and in the negative leading coefficient, we're going to have a maximum, as also indicated in the range. Okay, I'm going to leave the last function for you. It's called quintic. I can show you a graph here on my calculator. The red, okay, it resembles very much the same thing as a third degree polynomial, but it's even flatter around the origin. And when I transform it again, I get even larger or more bumps, okay, or we could say peaks and valleys. Okay, I'm going to let you graph those, and you can take a look at the functions that I've given you to graph that and fill in the specific terminology. Okay, what we're going to move on to is we're going to just try and identify, and you can obviously see my notes here, so you'll be able to pick it out, but we have 4 functions here. We're going to identify what types they are based off of their appearance. So we first want to look at question number 1. Which graph could represent a polynomial whose leading term is negative 3 times x to the fourth? I've already identified that it's b. If we look at b, it has an end behavior that is both negative. Okay, end behavior is the same, which means that we're talking about an even degreed polynomial. It has these extra bumps, unlike the parabola, which tells us that we're talking about a fourth degree polynomial. So we know it's going to be negative and a degree of 4. So our end behavior is negative, negative, faces downward, which tells we have a negatively coefficient, and then the general shape indicates a degree of 4. So that means that when we look at question number 2, we're looking at a positive 3 times x to the fourth. Obviously, that's going to be option D here. It's very similar to option B, but facing upwards. So the end behavior is positive, positive, indicating an even degree, and the fact that it's positive tells us we have positive leading coefficient. Then the general shape also indicates a degree 4 polynomial. Again, the fact that it looks kind of like a parabola but has these extra little bumps in them, that doesn't happen in parabolas, so it doesn't happen with our quadratic functions. So if we look at A and C then, question number 3 says which graph could represent a polynomial whose leading term is a positive 4 times x cubed. Okay, so positive leading coefficient, that means that our end behavior is going to be positive, which that happens here with a degree of 3. Okay, this looks sort of linear except for these extra little bumps, these peaks and valleys in the middle. That is what a third degree polynomial is going to look like. It's going to have a peak and a valley, and it has an end behavior that's negative and positive. So question 3 is going to be graph A, which means that the last one is C. A negative leading coefficient, which is why our end behavior is negative for this polynomial. Last thing here, identify the characteristics for each polynomial function. Create 2 different polynomials. First off, identifying what types they are. This first one is cubic because it is a third degree. Its end behavior is going to be positive, negative. We know that because with it being an odd numbered degree and its leading coefficient being negative, we know that its right end behavior is going to be negative. Its left is going to be the opposite of that, so it's positive. The number of possible x-intercepts with a third degree polynomial, I need to make an addition here, is just going to have either 1, 2, or 3 x-intercepts. Remember with odd degreed polynomials, you cannot have 0 x-intercepts. It's going to go through the x-axis and in at least one spot. Has no maximum or minimum, and based off of our constant term, it has a y-intercept of negative 1. Looking at the second function, at f of x, it is a quartic, okay, or a fourth degree polynomial. Because of its leading coefficient being positive, we know that the end behavior here is going to be positive, positive. Because it is degree of 4, we know that the number of possible x-intercepts is 0, 1, 2, 3, and 4. And now we also know that's going to be a minimum because this quartic function will be facing upwards. There will be some minimum value, and our y-intercept is 10. That concludes the characteristics of polynomials. We're going to be using those characteristics throughout this whole chapter and identifying polynomials and using that terminology to describe them. So your assignment is, I have already handed it out to you, is going to be that worksheet. It's due October 4th, so this coming Friday. And good luck. If you have any questions, feel free to talk to me in class.